Hello and welcome to the next video of our channel Practical Hope. In this video, we are going to do computational analysis of the behavior of a collection of particles in a box that satisfy Newtonian mechanics and interact via Lennard Jones Potential. We are going to take a system with a fixed number of particles, fixed volume and fixed total energy. We are going to do classical molecular dynamics simulations. So we are going to take a collection of particles in a box of size say Lx, Ly and Lz. First we have to set initial conditions. We have to specify the position of every particle. Now it can be done in two ways. Either particles can be uniformly distributed with equal spacing or they can be placed randomly provided no two particles overlap with each other. This second case in which we place particles randomly is difficult, so we will follow the first one, that is we are going to put particles uniformly. Then we have to give suitable initial velocity to all the particles. Equation of motion of individual particles is m d2r by dt2 equal to fi equal to minus gradient of potential. The potential we are going to take is the Lennard Jones potential, the details of which we will discuss later. We have to integrate such equations for all the particles and calculate new positions and velocities using velocity-Verlet algorithm. This velocity-Verlet algorithm also we are going to discuss later. We have to keep updating the positions and velocities with time. Once equilibrium is reached, we can evaluate the relevant statistical quantities. First, let's have an idea about the algorithm in the form of flowchart. Set the initial parameters or constants. The parameters or constants we are not defining here because we haven't studied all the parameters. We'll discuss them later while writing the main program. Then we have to initialize the positions x, y, z and velocities vx, vy, vz of the particles. Then we have to calculate initial total force on the particles. Then update the position of all the particles. Save old force and calculate new force on all the particles. Update velocities using old and new force. Then again we have to update the position of all the particles. These three steps we have to keep repeating till equilibrium is reached. Next, Lennard Jones potential. This is the expression. First term is the repulsive term, whereas the second term is the attractive term. This potential is between two particles separated by a distance r. Now if we plot this potential, we get a curve like this. Epsilon is the depth of the potential and sigma is the minimum distance that the two particles can come close. At distances less than sigma, potential will become positive and the forces between the particles will be too high and repulsive. Force is minus gradient of potential, so this will be the point of zero force, since here the change in potential is zero. On the right side there will be attractive force, and if the distance is decreased, then the particles will experience repulsive force. Suppose these are the two particles and this is the minimum that they can come together. So sigma is the center to center distance. Or in other words, we can also say that sigma is the diameter of the molecules or particles. We are going to consider distance in terms of sigma and energy in terms of epsilon. For simplicity, we are going to take both sigma and epsilon to be 1, but you can take it according to the particles you want to study. Next, initialize the positions. Let the dimensions of the cubical box are 20 by 20 by 20 sigma cube, since we are going to take distance in terms of sigma now. Sigma is 1, so dimensions will be 20 by 20 by 20. Distance between the two closest particles along the 3 axes is 2 sigma or 2. So if we place the particles uniformly, then they will look something like this. Since the program for molecular dynamics simulations is going to be lengthy, so we are going to divide it into small modules or functions. Let's write a function to initialize the positions. This is the code. We have defined a function. What we get at the output, x, y, z, position of the particles. The name of the function is POSINIT, short form for position initialization. P1 is the minimum coordinate along x or y or z axis. P2 is the maximum coordinate and dp is the difference. We have used 3 loops p, q and r varying from p1 to p2 with difference dp, and values of the positions will be p, q, r. kk we have to increase every time. Now P1 is 2 and P2 is 16. So along a particular axis there will be 8 points or 8 particles. So if we consider 3 dimensions, then there will be 8 by 8 by 8, that is 512 particles total. We are going to study a system of 512 particles, and this value of kk will change 512 times. Once we initialize the position, we have to initialize the velocity. We can choose random velocity. So vi is a random. Suppose we want to choose random velocity, but in both positive and negative direction. Then vi is a random minus 0.5. Rand is the function that will give values between 0 and 1. According to equipartition theorem, average kinetic energy per degree of freedom is kT by 2. Let Vx, that is velocity of the x component of any particle, is a random minus 0.5. Let x is rand. Then Vx is given by this expression. So average value of Vx square is given by this. We can solve this integral and evaluate the value of a. Let us assume that kt is 1 and m is also 1. So a is root 12. We'll discuss later in detail why this kt is 1 and why this mass is 1. Also, we have to make sure that some of the components of velocities of all the particles along the 3 axes should be 0. This is the code. First we have defined a function. Vx, Vy, Vz will be the output components of velocities of all the particles. Well init is the function name. First we have set a for loop that will vary from 1 to np. Np are the number of particles, that is 512 in the present case. Vxi is Va multiplied by rand minus 0.5. Va is the multiplier for the components of velocities, and this value of Va, as we have discussed earlier, is square root of 12. Similarly, Vy and Vz. Then we have to calculate the average velocity along the xyz directions. So we have used a for loop that will run from 1 to number of particles. Avx is the average velocity of particles along x-axis. So it is Vxi plus Avx. Initial value of Avx we will set to 0. Similarly, Avy and Avz, initial values of Avy and Avz will also be set to 0. When we set the constant, there we will set Avx, Avy and Avz as 0. Next, Avx is equal to Avx by Np. So now Avx will be the average velocity along the x-axis per particle. Similarly, Avy and Avz, and now we'll simply subtract this value of Avx from the velocity components of every particle. So we have to use another for loop that will also run from 1 to np, that is the number of particles. Vx is equal to Vx minus Avx, Vy is equal to Vy minus Avy, and Vz equal to Vz minus Avz. Finally, end function. So in this way, we are going to initialize the velocity components Vx, Vy, Vz for all the particles, and we have made sure that sum of the components of velocities of all the particles along the 3 axes is 0. So there is no net momentum along any direction. Next we have to calculate the force. So this expression and curve we have already discussed. Now force is given by minus gradient of potential, so it is magnitude of force into unit vector. Magnitude of force is given by this expression. We can easily differentiate the expression for potential and get the value of force. Now suppose these are the 2 particles and the distance between them is quite large. So force will be almost 0 or negligible. Now suppose they come close. So now there will be an attractive force, and once they come too close, then there will be repulsive force. Now as we discussed that if the distance between 2 particles is quite large, then the force between them will be negligible or 0. So what we are going to do is we are going to define a cutoff distance RC, beyond which the potential as well as the force will be 0. But now the potential has become discontinuous. To make it continuous, we can shift the potential upwards. Now the potential will be continuous. Fc is the critical force, that is the value of the force at R equal to Rc. So modified force is F minus Fc. We have to subtract this value of cutoff force. So now the value of this modified force will be 0 at R equal to Rc. force is minus gradient of potential. So we can calculate potential from this modified force by integrating the force. So if we integrate modified force, then we get potential like this, VR plus FCR. But we also want potential to be 0 at R equal to RC. So this is VC prime is the cutoff potential at R equal to RC, and we have to subtract this VC prime from V prime R. So modified potential is given by this expression. We can also write modified potential like this. So these are the expressions for force and potential that we are going to use in our program. Now to reduce the computation time, we can use this expression that Fij, force on particle I due to J, equal to minus Fji, that is force on particle J due to I, because of Newton's third law. It will help in less number of force calculations. Now suppose this is the simulation box. Obviously it's going to have a large number of particles, but suppose we consider 4 particles. Now we have to define what kind of boundaries we are going to take. Either we can take reflecting boundaries, which is quite impractical. So we are going to take periodic boundary conditions. Now it means that the simulation box will have a replica of it on all its sides with similar number of particles. Now suppose these are the coordinates of 4 particles in the main simulation box. Say R12 is the distance between them, and this distance R12 we can easily evaluate using this expression. Suppose we want to calculate the distance between particles 3 and 4 in the simulation box. So R34 should have been calculated like this, but no. Distance between particles 3 and 4 will not be as shown by the pink line, but will be as shown by the blue line. Since particle 4 in the adjacent box towards the left side of the main simulation box is closer to particle 3. Now how to calculate this R34 prime? Say this is Lx. Now if magnitude of dx34 is greater than Lx by 2, then dx34 prime is given by this expression Lx minus mod of dx34 multiplied by unit vector. We also have to put a unit vector. Why? Because force on particle 3 due to particle 4 in the simulation box will be towards right side, whereas if we consider particle 4 in the adjacent box, then force on particle 3 will be towards left side. So there is a inversion of the direction of the force, so we have to put a minus sign. So x cap can be written like this. So this is the expression for dx34. We have to do it in all the 3 directions, y and z. Once we have the value of dx34 prime, dy34 prime and dz34 prime, we can easily evaluate the value of the distance r34 prime, correct distance between particles 3 and 4. Now let's implement this force calculation in the SCILAB program. This is the function. Fx, Fy and Fz are the output, that is the components of forces on the particles. Pen is the total potential energy of the system. Name of the function is force calc. X, Y, Z are the inputs, because to calculate the force we need the positions. Fx initially we have assumed 0, so Fx equal to 0's NP comma 1. Similarly Fy and Fz, because initially we are considering force as 0, and then we'll add up force on any particle due to all other particles. Pen, total potential energy, is also considered as 0 initially. So we have used 2 for loops. First will run from 1 to NP minus 1, and the second will run from j equal to I plus 1 to NP. So we are going to consider the different pairs of particles, and we are not going to repeat a particular pair. Suppose if we have calculated the distance between 1 and 2, and then we can calculate the force, but then once we know F12, we don't need to calculate F21. That's why I has been varied from 1 to NP minus 1 and j has been varied from I plus 1 to NP. So we can evaluate x1, y1 and z1, and then x2, y2 and z2. Then we can calculate dx, dy and dz. Then we have to apply this condition. If absolute value of dx is greater than Lx by 2, then dx is given by this expression as we discussed earlier. Similarly, along the y-axis, if absolute value of dy is greater than L by 2, then dy is given by Ly minus absolute value of dy multiplied by minus dy by absolute value of dy. Similarly, along the z-axis. Once we know dx, dy, dz, we can easily calculate r, distance between particle I and j. So it is square root of dx square plus dy square plus dz square. Then we have to check whether this distance is less than the cutoff distance RC, because if the distance is greater than the cutoff distance, then force will be 0. We'll only calculate force if R is less than RC. So if R is less than RC, then the expression for force is given by this. Then we have to calculate modified force, F minus Fc. Then we'll calculate the value of the components of forces. So Fxi equal to Fxi plus Fm multiplied by dx by R. Actually, we have to add not the force but the component of force. So this dx by R is basically cos theta, that is the component of force along the x-axis. So we can calculate Fx, Fy and Fz. Now as discussed earlier that Fij is equal to minus Fji. So we can also calculate the force on the jth particle. So Fxj equal to Fxj minus Fm multiplied by dx by R. This minus sign is because the force on ith particle due to jth particle is in opposite direction due to force on jth particle due to ith particle. Next we can also evaluate the potential using this expression. Now we have to use the modified value of the potential Vm as we discussed earlier. Once we have Vm, we can add it to the value of the total potential energy. PEN is the total potential energy of the system. Next we have to update the positions and velocities of all the particles. Once initial positions, velocities and forces between particles are defined, we have to integrate the Newton's equation of motion for all the particles and evaluate their positions and velocities with time. This can be done by using velocity violet algorithm. We are not going into the details of this algorithm. We are only going to write the expressions for new positions and velocities. So this is the expression to calculate the position at time t plus delta t. We should know the value of the position at previous time t, velocity at previous time t and the acceleration at the previous time t. This is the expression to evaluate new values of velocities, that is velocity at t plus delta t. It can be seen from the second expression that we need both old and new values of forces while updating the velocities. So first we'll have to update the positions, then we'll save the old values of forces, then we'll calculate the new values of forces, and then only we will be able to calculate the new updated values of velocities of all the particles. Now after updating the position, we have to take care of one more point. It is possible that while updating the position of the particle, it can go out of the box. Since we are considering the periodic boundary conditions, so if a particle goes out of the box from the right, then another particle will enter from the left. We have to ensure it along all three axes x, y, z. Suppose this is the box and let these three are the particles. These are the dimensions Lx, Ly. Actually it's a three-dimensional box, but we are only considering two-dimensional for simplicity. Suppose this particle, while updating the position, it goes out of the box, then it should be put back as if it has entered from the left. It can be ensured by this expression. If xi is greater than Lx, then xi equal to xi minus Lx. Similarly, if the particle goes out to the left, then it should be put back here as if it has entered from the right side of the box. It can be ensured using this condition. If xi is less than 0, then xi equal to xi plus Lx. Similarly along the y-axis and similarly along the z-axis. So this we have to ensure while updating the positions. This is the code to update the position. X, y, z are the positions that we get at the output of this function. The name of the function is update pos. Then the inputs are x, y, z because we need to give the previous values of the positions, vx, vy, vz, velocity components and fx, fy, fz components of the forces. Then we have to use the for loop that will run from 1 to np, np being the number of particles. Then we have to calculate the new values of x, y and z using these expressions. T2 is dt square divided by 2m. Now we also have to make sure that the number of particles inside the box should be constant. So if xi is greater than Lx, then xi is equal to xi minus Lx. Else if xi is less than 0, then xi is equal to xi plus Lx. Similarly along the y and z axis. Finally end function. So this is the function to update the position. Next, function to update velocity. Vx, Vy, Vz are the new components of velocities. Ken is the sum of the kinetic energies of all the particles. Name of the function is update vel. The inputs are Vx, Vy, Vz and Fx, Fy, Fz. Fox, Foy and Foz are the values of the old forces. Fx, Fy and Fz are the values of the new forces. So we'll have to use a for loop that will run from 1 to np and calculate the new values of velocity components. T1 here is dt or delta t divided by 2m. We have got the values of the velocities, so we can calculate the value of total kinetic energy. So Ken is 0 initially, then we have used a for loop I equal to 1 to np, then Ken equal to Ken plus half Vx square plus Vy square plus Vz square. M we have already taken 1, finally n function. So this is the function to calculate the updated velocities of all the particles. Now this will be the main program. So first we are going to initialize the position xyz equal to pos init. Then we can save the initial position. So we can see how the particles have been placed initially. So x1 equal to x, y1 equal to y and z1 equal to z. Then we have to initialize the velocities. So Vx, Vy, Vz equal to vel init. Then we have to do force initialization. So Fx, Fy, Fz, comma Pen equal to force calc, comma force calc bracket x, comma y, comma z. So we have got the initial positions, velocities and components of forces along with the potential energy of system as a whole. This is the rest of the program. We have to use a for loop that will run from 1 to ni. Ni are the number of iterations, number of times we have to calculate the new or updated values of positions and velocities. So first we have calculated the updated positions using function update pos. Then we have saved the values of the old forces. So Fox is Fx and Foy is Fy, Foz equal to Fz. Then we'll calculate the new values of forces using function force calc. So now we have both the old forces Fox, Foy, Foz and the new forces Fx, Fy, Fz. So we can evaluate the updated velocities using function update vel. Pen is the total potential energy of all the particles and Ken is the total kinetic energy. We can calculate Pe, that is average potential energy per particle, and Ke, average kinetic energy per particle. We are also saving the number of iterations in a vector, say nit. So nit bracket k equal to k. Then display iterations string k. Finally, how to check the correctness of the code. Since we are studying NVE system, so total energy of the system should be conserved. Kinetic energy and potential energy can vary. Next, let's move on to the main SCILAB window to write the main program. We have already discussed everything, so it's already written. First, the title of the program, Molecular Dynamic Simulation in 3D NVE System. CLC, Clear and CLF we have already discussed many times in our previous videos. Let's discuss the constants first. Sigma, we have taken 1, epsilon 1, mass of the particles 1, Lx 20, Ly equal to Lx and Lz also equal to Lx. So we have taken a cubical box. Np, number of particles 512, we have already discussed it while initializing the positions. Ni, number of iterations. Ni should be large so that we give ample time to the system to reach equilibrium. However, it should not be too large. Otherwise, you need a lot of time to simulate the program. dt 0.005. For more accuracy, you can take dt less also. Va, multiplication factor for the velocities as already discussed, is root 12. Rc, the cutoff distance 2.5 sigma. Sigma is 1, so Rc is 2.5. Avx, Avy and Avz, as we already discussed during velocity initialization, are the sum of the velocities, average velocities along the x, y and z axis. T2 is dt square divided by 2m and T1 is dt by 2m. Fc is the cutoff force, Vc is the cutoff potential. This is the function to initialize the position. We are not discussing it again. Next is the function to initialize the velocities of all the particles. Then function to calculate the forces, then function to update the position, finally the function to update velocity. This is the main program. This also we have discussed. Next we have to plot. We are going to plot first initial positions of the particles, then final positions of all the particles. Then we are going to plot average kinetic energy per particle, average potential energy per particle and total energy per particle. And finally we are also going to plot Maxwell speed distribution curve. So first subplot 2, 2, 1, scatter 3D, x1, y1, z1, fill, x1, y1, z1 are the initial positions of the particles. Replot 0, 0, 20, 20. So basically we are fixing the size of the box. Title, initial positions of the particles, font size 6. Then subplot 2, 2, 2, scatter 3D, x, y, z, x, y, z are the final positions of the particles. We have already calculated kinetic energy and potential energy per particle. So T is the total energy equal to Ke plus Pe. Subplot 2, 2, 3. Then we have to plot all the three energies, that is kinetic energy, potential energy and total energy with number of iterations NIT. Legend kinetic energy, potential energy, total energy. X label number of iterations with font size 6 and Y label energy with font size 6. Now we can calculate the net velocity of all the particles. So for I equal to 1 to np, velocity equal to square root of vx square plus vy square plus vz square. Now subplot 2, 2, 4. We are going to plot histogram. So hist plot 20, velocity, polygon equal to percentage t. This 20 is the class. Basically we are going to divide the whole range of velocity of particles into 20 equally spaced classes. Finally x label speed of the particles with font size 6. Let's run this program. So as you can see, iterations 1, 2, 3, 4. It is going to take a lot of time and my PC took about 30-40 minutes to run this code. So we are skipping this simulation time and let's see the final result. So these are the initial positions of particles. Then these are the final positions of the particles. Third plot is the energy. Kinetic energy initially is increasing, but then it reaches the equilibrium and is fluctuating about some average value. Potential energy initially is decreasing and then once it reaches the equilibrium, it is also fluctuating around the average value. Total energy is fixed and the fourth plot is the Maxwell speed distribution curve. Now this fourth plot is not perfect. You can improve it by increasing the number of particles and by increasing the number of iterations. But of course, if you increase the number of iterations, then you will need more time to simulate the program. So these are the 4 plots. Now there are some issues that we have not touched. What does KBT1 signify and why mass is 1? How we can get the results for the actual molecules? All this we'll discuss in the next part of this video. In this video we have studied NVE system. We can also study NVT system. That also we are going to study in our next video. Finally, this simulation is taking a lot of time, which obviously we can reduce. There are ways to reduce the computation time by different concepts that we will discuss in the next part of the video. If you like it, share it with your friends and colleagues and don't forget to subscribe our channel if you haven't done it yet.